In less than a year, the James Webb Space Telescope, JWST, has dramatically transformed our understanding of the universe. Launched on December 25, 2021, its groundbreaking observations have astonished both experts and the general public. Far surpassing its predecessor, the Hubble Space Telescope, the JWST is poised to advance our comprehension of cosmic phenomena to unprecedented levels. This $10 billion marvel, designed specifically for infrared astronomy, offers glimpses into the universe's earliest stages, moments following the Big Bang during the so-called Dark Ages. However, some of the data it has transmitted to Earth-based research stations have raised significant questions. Certain observations appear to challenge the prevailing cosmological model, forcing us to reconsider the very origins of our universe. Could it be that our foundational understanding of the cosmos needs to be re-examined? Revisiting the Big Bang theory. To understand the implications of the James Webb's discoveries, we must first revisit the Big Bang theory. According to the standard cosmological model, the Big Bang was not a conventional explosion in space but rather the expansion of space itself, along with the emergence of matter and time, from a singularity, a point of infinite density and gravitational force. The evidence supporting this theory includes the discovery of cosmic microwave background, CMB, radiation, remnants of the universe's early hot, dense state. Approximately 380,000 years after the Big Bang, the universe cooled enough for neutral hydrogen to form, decoupling matter and radiation. This marked the universe's transition to transparency, allowing the CMB radiation to propagate freely, a relic we can still detect today. The Big Bang theory explains the universe's evolution following its formation, but it doesn't address the singularity or what occurred before it. As our understanding of physics is limited in such extreme conditions, these gaps leave room for scrutiny and alternative interpretations. Challenging observations from the James Webb Telescope. The James Webb Telescope's cutting-edge instruments have provided unprecedented views of the universe's early structures. However, these observations have introduced anomalies that conflict with established cosmological expectations. One such challenge comes from the telescope's images of ancient galaxies. Contrary to predictions, these galaxies appear remarkably small and uniform, even those believed to be larger and more massive than the Milky Way. The finding contradicts the assumption that older galaxies should appear distorted or more chaotic due to mergers and collisions in the universe's formative stages. Additionally, some of these ancient galaxies exhibit star populations that seem over 1 billion years old, older than the universe itself according to the timeline established by the Big Bang. If these observations are accurate, they suggest that the universe may not have originated from a singular explosive event. The debate over a non-expanding universe. Another surprising outcome of Webb's data is the potential re-evaluation of the universe's expansion. According to the Big Bang theory, the universe has been expanding since its inception, with redshift measurements supporting this notion. However, some researchers argue that these redshifts may not indicate expansion but instead result from other phenomena. Proponents of a static universe, such as Eric Lerner and Ricardo Scarpa, have long questioned the expansion model. Their analysis of Hubble images suggested that redshifts could be consistent with a non-expanding universe. Webb's findings, including unexpectedly consistent galaxy shapes across vast distances, have reignited discussions about this alternative model. What does this mean for cosmology? While these discoveries are exciting, they are not definitive evidence against the Big Bang theory. Instead, they highlight the complexity of the universe and the need for further investigation. Current models, including the Big Bang, are built on decades of observation and experimentation. However, science evolves as new data becomes available, and anomalies like those revealed by the James Webb Telescope serve as opportunities to refine our understanding. It's important to note that scientific theories are not immutable truths but frameworks for explaining observed phenomena. The geocentric model, once widely accepted, was eventually replaced by the heliocentric model. Similarly, our current cosmological theories may one day be supplanted by more comprehensive explanations. Conclusion. The James Webb Space Telescope has opened a new chapter in our exploration of the cosmos. While its discoveries have raised questions about the Big Bang theory and the universe's expansion, they also underscore the importance of remaining open to new ideas. As researchers analyze Webb's data and conduct further observations, our understanding of the universe's origins and evolution will continue to deepen. Whether the Big Bang remains the cornerstone of cosmology or gives way to new paradigms, one thing is certain: the quest for knowledge is far from over. The current proposition presents 16 inaccurate predictions and only one correct one. For example, the Big Bang Theory's prediction for the abundance of helium deviates by a factor of 2, and its prediction for the abundance of lithium is off by a factor of 20. Only the prediction for the abundance of deuterium, an isotope of hydrogen, is accurate. Despite the vast distances involved that diminish optical effects, there are structures in the universe that, based on our understanding, are far too massive to have formed within the timeframe since the Big Bang. Moreover, incorrect predictions about the density of matter in the universe and peculiar inconsistencies in the cosmic microwave background, CMB, challenge the very foundation of the Big Bang Theory. Given these contradictions, one might wonder why this cosmological crisis receives so little attention in mainstream media. Advocates of alternative theories argue that they are marginalized by the dominant scientific consensus. They claim that scientists who genuinely question the Big Bang Theory are often dismissed as uninformed or incompetent, and their work is rarely supported by funding or given serious consideration. On the other hand, the prevailing view highlights that findings from advanced observations, such as those from the James Webb Space Telescope, JWST, require rigorous analysis. For instance, while ancient galaxies are expected to appear more chaotic due to past interactions, the age and structure of these formations must be carefully verified. Some initial findings suggest these ancient galaxies are unexpectedly well-ordered, resembling modern spirals and disks, raising fundamental questions about galaxy formation mechanisms. Further puzzles arise in determining the ages of these galaxies. Stellar populations in some appear much older than expected, over 1 billion years older than the conventional timeline derived from the Big Bang Theory. This anomaly challenges the notion that nothing could predate the Big Bang, as well as the assumption that all structures must have emerged after it. Another contentious point is the interpretation of cosmic expansion and redshift phenomena. The Big Bang Theory posits that the universe is expanding uniformly, with galaxies moving away from one another at speeds proportional to their distance. This expansion is reflected in the redshift of light from distant galaxies, where wavelengths stretch towards the red end of the spectrum. However, alternative theories propose that redshift might not solely result from cosmic expansion but could also stem from other factors, such as intrinsic galaxy properties or variations in the speed of light over vast distances. Critics of the Big Bang Theory further cite discrepancies in predicted abundances of elements like helium and lithium, suggesting that our understanding of the early universe might be incomplete or flawed. While the theory successfully explains many observed phenomena, its predictive accuracy is limited in critical areas. Additionally, the CMB, a cornerstone of the Big Bang model, has faced scrutiny. Irregularities in its distribution and intensity have prompted questions about the uniformity and isotropy expected from a homogeneous universe originating from a single event. Ongoing research and future space missions, such as the European Space Agency's Euclid mission and upcoming NASA projects beyond JWST, aim to probe these mysteries further. At the same time, theoretical physics continues its quest to reconcile quantum mechanics and general relativity into a unified framework capable of explaining the conditions at the universe's origin. The Big Bang singularity represents a breakdown in current physics, where gravitational forces become infinite, and classical laws cease to apply. Advancements in technology, computational simulations, and interdisciplinary collaboration provide unprecedented opportunities to challenge and refine existing theories. Beyond the scientific community, cosmological theories also influence philosophical and religious discussions, shaping humanity's understanding of its place in the cosmos. The Big Bang Theory remains the dominant explanation for the universe's origin and evolution, but it is not without controversies and challenges. Observations made possible by tools like JWST push the boundaries of knowledge, forcing us to revisit fundamental assumptions and explore alternative explanations. The dynamic interplay between observation, theory, and interpretation underscores the ever-evolving nature of scientific inquiry and our shared quest to unravel the mysteries of the universe.